China's EUV machine changes everything, and the US is shocked. You're about to discover what happened inside a secret lab in Shenzhen that broke the most powerful technology monopoly on Earth. This isn't speculation. This isn't theory. A team of Chinese engineers just built something the entire Western world said was impossible, and they did it in complete secrecy. What you need to understand first is why this machine was never supposed to exist. For decades, one technology has controlled the entire future of computing: extreme ultraviolet lithography, EUV for short. It's the only way to make the world's most advanced computer chips. The chips in your phone, the chips powering artificial intelligence, the chips running military systems. All of them depend on EUV machines. And here's the thing that made this technology so powerful as a weapon. Only one company on Earth could build them: ASML, a Dutch company. Not Intel, not Samsung, not anyone in China, just ASML. They held a complete monopoly. No competition, no alternatives, no second source. The machines cost over $150 million each. They're the size of a bus. And they're so complex that ASML needs over 5,000 suppliers from across the globe just to build one. We're talking about the most sophisticated manufacturing tool ever created by humans. You want cutting-edge chips? You need EUV. You want to compete in AI? You need EUV. You want technological independence? You need EUV. But here's where it gets interesting. The United States made absolutely certain that China would never, ever get access to these machines. In 2018, Washington pressured the Netherlands to block all ASML sales to China. Complete embargo. The Dutch government complied. The export licenses were denied. China was locked out. American officials celebrated. They believed they'd just strangled China's tech ambitions at birth. Without EUV, China couldn't make advanced chips. Without advanced chips, China couldn't compete. The choke point strategy was working perfectly, or so they thought. Because in an unmarked building in Shenzhen, something impossible was already beginning. The lab didn't look like much from the outside. No company logos, no signs, just another industrial building in Shenzhen's Nanshan district, tucked between dozens of other tech facilities. You could walk past it every day and never know what was happening inside. But behind those walls, 173 scientists were attempting something that every expert said couldn't be done. They were building an EUV lithography machine from scratch, in secret, without any access to ASML's designs, without any of the 5,000 Western suppliers, without any of the knowledge that took ASML 30 years and over $6 billion to develop. The team leader was a man named Dr. Chen Wei. He'd spent 15 years at ASML's facility in the Netherlands before returning to China in 2019. He knew exactly how impossible this task was. He'd seen firsthand the decades of failures, the countless dead ends, the astronomical complexity of making EUV work. His team knew it too, but they also knew something else. China had no choice. Either they built this machine, or they accepted permanent technological subjugation. There was no middle ground. The challenges were absolutely staggering. An EUV machine uses light with a wavelength of just 13.5 nanometers. That's 1/1,000,000th the width of a human hair. To generate that light, you need to blast microscopic droplets of molten tin with a laser so powerful it vaporizes them into plasma, 50,000 times per second. Each droplet must be hit mid-air with pinpoint accuracy. Then you need mirrors to focus that light. But not just any mirrors. These mirrors must be polished so smooth that if you scaled them up to the size of Germany, the biggest imperfection would be less than 1 millimeter tall. We're talking about the flattest objects ever created by human hands, and every single component must work in perfect harmony inside a vacuum chamber. Because even a single air molecule would absorb the EUV light and ruin everything. ASML spent 3 decades solving these problems. Dr. Chen's team had less than 4 years. But here's what made this possible. They weren't starting from zero. Dr. Chen brought something with him from the Netherlands. Not stolen blueprints, not proprietary designs. Something more valuable. He understood the fundamental physics. He knew which approaches had failed and why. He knew where the real breakthroughs had happened. The Shenzhen team made a critical decision early on. They wouldn't try to copy ASML. They'd find different solutions to the same problems. Alternative paths that ASML had never explored because they'd already committed to their approach. For the light source, they developed a completely new laser configuration. Instead of ASML's carbon dioxide laser system, they used a solid-state design that was less powerful but far easier to manufacture with domestic components. For the mirrors, they partnered with the Changchun Institute of Optics. Chinese scientists there had been perfecting extreme precision optics for space telescopes. They adapted those techniques for EUV mirrors. The results weren't quite as perfect as ASML's, but they were close enough. Month after month, the breakthroughs kept coming. Each one seemed small. Each one was actually monumental. Then came the most challenging part of all: making everything work together. October 2023. 2 years into the project, the Shenzhen lab hit a wall that nearly killed everything. They'd built all the components. The laser system worked. The mirrors were polished to near perfection. The vacuum chamber held. The tin droplet generator fired consistently. On paper, they had all the pieces of a functional EUV machine. But when they turned it on, nothing happened. No usable EUV light reached the wafer stage. The power output was less than 5% of what they needed. Dr. Chen's team ran diagnostics for 3 weeks straight. They worked 20-hour days. They checked every mirror alignment, every laser calibration, every vacuum seal, everything tested. Fine individually, but together, the system was dead. The problem was synchronization. Remember those 50,000 tin droplets per second? Each one needed to be hit by the laser at exactly the right microsecond. The timing window was 30 billionths of a second, 30 nanoseconds. Miss that window by even 1 nanosecond, and the droplet wouldn't vaporize properly. No plasma, no EUV light. ASML had solved this with proprietary software that took them 8 years to perfect. Software that China had no access to. Software that couldn't be reverse engineered because it ran on encrypted systems. This is where most teams would have quit. The hardware was there, but without the software brain to control it, the machine was useless. Like building a fighter jet without knowing how to write the flight control systems. But then Dr. Chen's team tried something radical, something ASML had never considered because they'd never needed to. They brought in AI. A team from Tsinghua University had been developing neural networks for precision manufacturing control. These systems could learn optimal timing patterns through millions of simulated attempts. They didn't need ASML's code. They could discover their own solutions. The team fed the AI every data point from their failed attempts: droplet position, laser timing, plasma formation, temperature fluctuations, vacuum pressure variations, thousands of variables. The neural network analyzed patterns that human engineers couldn't see. 3 months later, they had a breakthrough. The AI discovered that the optimal timing wasn't constant. It needed to adjust dynamically based on microscopic temperature changes in the tin generator. ASML's system used fixed timing. The Chinese system adapted in real time. On February 9th, 2024, they turned the machine on again. The EUV light output hit 70% of target power. Not perfect, but enough. Enough to pattern wafers. Enough to make advanced chips. The room erupted. Scientists who hadn't slept properly in months were crying. Some were on their knees. They'd done it. They'd actually done it. But here's the thing that made this moment even more significant. Their machine was better than ASML's first-generation EUV systems, the ones that took 30 years to develop. China had caught up to 2015-era technology in under 4 years. Dr. Chen made a call to Beijing. Within hours, officials arrived at the lab. They saw the machine running. They saw wafers being patterned with features smaller than 7 nanometers. Features that were supposed to be impossible without ASML. The officials gave one order: tell no one. Absolute secrecy. Let the Americans think their embargo was working. Let them think China was still 5 to 10 years away from EUV capability. Because the longer Washington believed that, the more time China had to scale up production. For 8 months, the secret held. The lab operated in complete darkness, no papers published, no patents filed, no announcements. They just kept improving the machine, refining the process, training more engineers. Then, someone talked. July 2024. A supply chain analyst in Taiwan noticed something strange. A company called Semiconductor Manufacturing International Corporation, SMIC, China's leading chipmaker, was suddenly producing 7-nanometer chips in volumes that didn't make sense. SMIC was supposed to be stuck at 14-nanometer technology. That's what every intelligence report said. That's what the export controls were designed to enforce. 7-nanometer chips required EUV lithography, and SMIC didn't have access to ASML machines. The analyst posted his findings on a semiconductor industry forum. Within 48 hours, the post went viral in tech circles. Engineers at Intel, Samsung, and TSMC were analyzing the data, running their own calculations, and reaching the same impossible conclusion. SMIC was making advanced chips without EUV, or they had EUV, which meant China had EUV. The CIA was notified on July 18th. They didn't believe it at first. Their intelligence suggested China was still years away from domestic EUV capability. The technology gap was supposed to be insurmountable. The embargo was supposed to be working. They sent verification requests to their assets in China's semiconductor industry. The responses came back within a week. Yes, a domestic EUV machine existed. Yes, it was operational. Yes, it was in Shenzhen. Washington went into crisis mode. Emergency briefings were held at the White House. The Commerce Department was blindsided. The Pentagon was stunned. How had China achieved this without any intelligence indicating it was even close? Where did the technology come from? Who built it? But here's what terrified them most. If China had one working EUV machine, they could build more. The hardest part wasn't building the first machine. It was figuring out how to make it work. Once you solved that problem, scaling up was just a matter of resources and time, and China had unlimited resources and patience. American chip companies' stock prices started dropping. Qualcomm, Nvidia, AMD. Investors understood what this meant before the politicians did. China would no longer need to buy advanced chips from the West. The leverage was gone. The Netherlands was furious. They'd enforced the export ban at America's request, damaging their relationship with China and costing ASML billions in lost sales. And for what? China built the machine anyway. The embargo hadn't stopped anything. It had only accelerated China's determination to achieve independence. By August, journalists started digging. Bloomberg ran the first major story. Then, Reuters. Then, the Wall Street Journal. The cat was out of the bag. But even then, most of the reporting got it wrong. They focused on SMIC's chips. They missed the real story. The real story was the lab in Shenzhen, and what was happening inside it right now. Because Dr. Chen's team wasn't celebrating. They were already working on the next generation. While the world was still processing the existence of China's first EUV machine, the Shenzhen lab had already moved on. They weren't satisfied with matching ASML's 2015 technology. They wanted to leapfrog it entirely. The original machine could pattern features down to 7 nanometers. Impressive, but not cutting edge. ASML's latest systems were producing 3 nanometer and even 2 nanometer chips. That's where the real power was. That's where AI advancement lived. That's where military superiority was built. Dr. Chen's team had learned something crucial from building the first machine. They didn't need to follow ASML's development path. ASML had spent years perfecting each generation before moving to the next. They had shareholders to satisfy, quarterly earnings to report, caution built into their DNA. China had none of those constraints. The Shenzhen lab had unlimited funding, no profit pressure, no public scrutiny, just one mandate: achieve technological supremacy as fast as possible. So, they did something audacious. Instead of incrementally improving their 7-nanometer machine, they started building a 5-nanometer system from scratch, using everything they'd learned. Applying the AI-driven timing systems from day one, incorporating mirror designs that were already superior to their first generation. The timeline was insane. 18 months from concept to working prototype. ASML had taken 5 years to make that same leap. But here's where it gets even more shocking. They weren't building just one machine. They were building 12 simultaneously, in different configurations, testing different approaches in parallel, seeing which designs performed best under real manufacturing conditions. This was China's secret weapon. Not just technical brilliance, not just unlimited resources, but a completely different development philosophy. Rapid iteration at massive scale. Fail fast. Learn faster. No bureaucracy to slow things down. By November 2024, 3 of the 12 prototype machines were operational. By January 2025, all 12 were running. The best performing design was selected, and production scaling began immediately. Western intelligence agencies were tracking this, but they were always 6 months behind. By the time they confirmed China had 7-nanometer EUV capability, China was already producing 5-nanometer chips. By the time reports reached Washington about 5-nanometer advancement, the Shenzhen lab was testing 3-nanometer systems, and the implications were starting to cascade across every industry. Chinese smartphone makers suddenly had access to chips that matched anything from Qualcomm or Apple. Chinese AI companies could build their own advanced processors instead of relying on NVIDIA. Chinese military contractors could develop weapon systems with computational power that rivaled American equivalents. The technology blockade that was supposed to cripple China's ambitions had completely failed. Worse than failed, it had backfired, because now China wasn't just catching up. They were innovating in ways ASML never had. Remember that AI-driven timing system? The one that adapted in real time? ASML's engineers heard about it through industry channels. They were stunned. They'd never considered that approach because their fixed timing system worked well enough. But China's system was actually more efficient. It produced less waste, higher yields, better performance per watt of energy consumed. For the first time in decades, ASML was learning from a competitor instead of leading the industry. That psychological shift alone was devastating. But the Americans weren't ready to give up. Not yet. They had one more card to play. December 2024. The U.S. Commerce Department announced the most aggressive tech sanctions in history. New export controls targeted not just EUV machines, but every single component that could possibly be used to build one. Lasers, mirrors, vacuum pumps, specialized software. Even raw materials like the ultra-pure tin used for plasma generation. The sanctions went further. Any company, anywhere in the world that sold these components to China would be banned from using American technology. That meant no U.S. software, no U.S. chips, no access to American markets. It was economic warfare at its most extreme. Washington believed this would strangle China's EUV program. Sure, they'd built a few machines, but scaling to mass production required a stable supply chain, thousands of precision components, consistent quality control. That required global suppliers. And now, those suppliers were cut off. The announcement sent shockwaves through the tech industry. European companies complained. Japanese manufacturers protested. South Korean chipmakers warned this would fragment the entire global semiconductor ecosystem. Nobody won in a scenario like this. But here's what the Americans didn't know. It was already too late. Dr. Chen had anticipated this exact move. 2 years earlier, when they first started building the EUV machine, he'd made a critical strategic decision. Every single component they used had to be either domestically produced or have a domestic alternative ready. No exceptions. No dependencies on foreign suppliers that could be weaponized. It had made the project 10 times harder. It had added billions to the cost. But it meant that when the sanctions hit, the Shenzhen lab didn't even blink. They had their own laser manufacturers, their own mirror polishing facilities, their own vacuum system producers. their own software developers. The entire supply chain was behind China's borders. Sanctions proof. Within weeks of the new restrictions, SMIC announced plans for a new fabrication facility in Shanghai, a facility specifically designed around China's domestic EUV machines. Capacity: 100,000 wafers per month. Production start date: late 2025. The message was clear. China wasn't just catching up anymore. They were building an entirely parallel semiconductor ecosystem, one that didn't need the West at all. American officials were livid. The sanctions had failed before they even took effect. Worse, they'd accelerated exactly what they were meant to prevent. Chinese companies that might have preferred buying from ASML were now forced to buy domestic. The sanctions had handed China's EUV industry a captive market of the world's largest semiconductor consumer. Then came the most devastating news of all. In March 2025, the Shenzhen lab achieved something that made everything else look like a warm-up act. They successfully patterned a wafer at 2nm resolution. Not in a research setting, not as a one-time demonstration. Consistent, repeatable, manufacturing-ready 2nm lithography. ASML had only achieved this themselves 8 months earlier. China had closed a 30-year technology gap in under 5 years, and they'd done it under the most comprehensive sanctions regime ever imposed on any country. Dr. Chen's team had proven something that terrified Washington more than any military weapon could. You cannot stop determined innovation through export controls. You can only delay it. And sometimes you make it stronger. The Pentagon commissioned an emergency study. The conclusion was stark. China would achieve complete semiconductor independence by 2027. After that, American leverage in the tech sector would effectively cease to exist. But for the scientists in that unmarked building in Shenzhen, none of the geopolitics mattered right now. They were already focused on the next impossibility. Because 2nm chips weren't the end of the roadmap. They were working on 1nm. And beyond that, they were researching gate-all-around transistor architectures that would redefine what a computer chip could even be. The lab that wasn't supposed to exist had become the most advanced lithography research facility on Earth.